we're comparing 3 cycles that have the same boiler pressure, 10 megapascal, and the same condenser pressure, 10 kilopascal. So you can try to sketch them all on the same TS diagram. The Carnot is going to look like the box under the dome. True? The ideal Rankine will have the same corner here, move over, up a little bit, and there, that finishes it out. True? So that's the ideal Rankine with no superheat. And now with superheat, you push it out to here, comes down. That's a bad looking down, sorry about that. Let me do this. Scoot it like this. All right, come down, still be two-phase, come across, condense, go up to the same point, etc. Okay. If you do that, the turbine work, it's greater, isn't it? Why is that? You're really coming in with high energy, steam coming in. It's a lot higher enthalpy. The condenser, well, you're condensing more. So this the amount of heat rejected per kilogram going through the condensers increased, hasn't it? How about the pump work? No change. You're still taking that saturated liquid and boosting it up from 10 kilopascal to 10 megapascal. How about the boiler heat transfer? Well, you're bringing in all of this the same, this is the same, but a lot more. So you've increased the boiler heat transfer. How about QNet and WNet? They're both the same, which is a good check. Almost always, when you work problems, you want to look for places where you can check your work, and if things don't sum up, then you know, oh, I must have made an error, where to look for an error. And then you'll use this WorkNet in the thermal efficiency calculation. Take a look at the thermal efficiency. Did it improve? Yeah, it improved a little bit. Will it ever get as high as a Carnot? Will it ever exceed the Carnot? It never will. But you're going to inch toward that 45%. Now, if you change your boiler pressure and condenser pressure, yes, you can change that efficiency. But leaving those the same, you've improved the system. Now, somebody may look at that and say 37.2 to 39.3. That's a huge percent difference in the performance of these systems. It may not look big, but it is a very big improvement. How about the back work ratio? It's even better. It's even dropped a little bit. Why? Because the turbine produces so much more. The work of the pump is the same, but the turbine produces so much more. What about pushing it? Somebody says, why stop at 440? Why don't we go out to 600 degrees C for superheat? Would that improve the system's performance? It really would. And so it goes out to 41%, 41.7%. And just like a good aspiring engineer, a good engineer, you always push it to the limit. But what type of limit are we going to start to go if we keep marching up in this temperature? It won't be a thermodynamic limit per se. It'll be a materials limit. Yeah, metallurgical typically. Things get they can't withstand the stresses. They're not as strong. They're not as durable at those high temperatures. So in the turbines, you'll have to have some special heat treatment of particular key components and making of super alloys and very expensive, but they'll try to continue to push this up. From a thermodynamic point of view, it's great. The thermal efficiency will incrementally go up and improve. So take a look. The turbine work is going up. The pump's not changing at all, is it? And how much heat is being dumped into the boiler is going up. Condenser, yes, you're dumping more heat out per kilogram that moves through, etc. So, and the back work ratio even improves.